Hello everybody and welcome back to Environmental Science 101. This week we get our hands dirty. Haha. Right, so there's me on the first slide. What are our objectives trying to get done? We are talking about the flow of energy and nutrients through biological systems or ecosystems. We are going to look at the interrelationships between organisms, which doesn't just come down to feeding, although feeding is a big part of it. We'll talk about the flow of nitrogen and carbon, both through living things and the non-living parts of the world. We'll talk about soil and how soil relates, get into the details of what soil is, where it comes from, and what it's made of. And finally, we will look at the role of human beings, how we impact the soil to meet our needs, and how sometimes those practices and incentives lead to destruction that end up costing us in the end. What are the sections going to be? So there are 6 for this unit. We've got energy in the ecosystem and community relationships, which are very much ecological units to start. We do our nitrogen cycle and carbon cycle, and then finally we focus on soils and then soil pollution towards the end. So let's get right into it. So our first section is on energy. So we have got these animals in our ecosystem, right? And we have our question, where does the energy come from? Well, these things, animals, are open systems. They are constantly exchanging matter and energy with all the stuff around them, the living stuff around them and the non-living stuff. So we're going to say for now that we're getting all of our energy from food. We're also getting nutrients from food, but for now we focus on the energy part of it, right? So we eat something to get that food out. Now, energy, I've got a standard definition up here that I don't love. Ability to do work or cause change, I think that's fine. We're going to talk about 3 forms, kinetic, potential, and chemical. Chemical really being a form of potential energy. We've got fire over here, a chemical reaction which releases energy. And we should know that energy is not going to be created or destroyed as part of this process, but it's just going to move from one form to another, move from one place to another. There is one definition for energy that I really like, courtesy of our own Phil Root. The non-stuff, in stuff, the make stuff, do stuff. That definition is the best. We can remember that. Okay, kinetic energy. Kinetic as in motion, energy of movement, right? This person putting out a lot of kinetic energy right now. So this would include temperature and thermal energy, which is going to be the motion of little molecules. And the more those little molecules move, the hotter they are, the more thermal energy, right? So when a bunch of molecules that are moving really quick, right, in a hot pot of water, right, come into contact with something else, they transfer that energy, and maybe they transfer it too quickly, right? That is a thermal energy transfer. We call that heat. Potential energy, however, is going to be the opposite. Stored energy, not being used for movement. Stored energy due to position, like our ball at the top of the hill. So we could transform this energy into something else by pushing the ball down, at which point we have transformed the energy from one form to another, from potential to kinetic. So this is going to be our type example, right? Whenever you think of potential energy, you imagine the ball at the top of the hill just ready to roll down and release a bunch of energy along the way. Or maybe you can picture a dam full of water, right? And what happens when it breaks? It releases all this energy that was stored up due to the position of the water, which is now falling. Now, chemical energy is actually going to be a form of potential energy, but it's so common and kind of special that we make it its own thing, right? So this is going to be the energy inside food, right? It's stored in the chemical bonds. We eat it, our body transforms it into other molecules or whatever kind of energy that we need, right? Like our runner, turning this kind of energy into kinetic energy. And in the process, we release heat. So our organisms are also going to have to store energy for later, and transforming the food molecules from one form to another is going to be part of that process. Okay, so I have this as an example. We don't need to worry about all the details here, right? But this is what a sugar molecule looks like. It's got all this energy stored up due to its bonds, saving it for later. Now, we see that energy changes into other forms, right? We can break our dam and turn potential energy into kinetic. We can have our car, which turns chemical energy stored in the gasoline into kinetic. Or in this case, our person, right, who turns chemical energy from food into energy of motion. And these are all going to be energy transformations that we're looking at. Just as an example, something that I always remember, right? So a gallon of gasoline has about 31,000 calories in it. 31,000 kilocalories for the unit we're using, right? And we might imagine, right, we can use this 1 gallon of gas in some kind of car to go, I don't know, 20, 25 miles, depending on factors, right? Well, we might think that a car is really efficient at using energy, And in some ways it is, and it's gotten better over time, but it is nothing compared to a human being, right? So a human being off of a sandwich, right, that's 500, 1,000 calories, if they're properly trained and in shape, can run like 20 miles. In other words, we've got a factor of about 30. This person is way more than 30 times more efficient, right? But a trained person of any kind, right, could easily be far more energy efficient than our cars. Your body really is amazing. It is so incredibly good at doing this. We talked about this a little bit earlier, right? That, there's energy lost along the way when we transform from one form to another. And where does that extra energy go, right? Well, we talked about the car being less efficient than the person when we transformed energy from one form to another. And what we're really talking about, right, is how much of the energy is lost in the transformation. And when it's lost, it turns into heat, which is not a very usable form of energy, right? So we can imagine our gasoline vehicle here, right? We've got gasoline going in, right? That's our 100% to start. So in a typical case, most of it is actually going to be lost directly due to heat, due to inefficiencies in the engines, right? Some of it is going to be used in other parts of the car, but ultimately only something like a quarter of it is actually going to get translated into the movement. There's so much heat loss along the way, and this is inevitable, right? You can never have a perfect system for transforming energy from one form to another. It's also the reason why things cannot run and move forever. So, we can talk about energy transfer now in the context of ecology, right? That first image we had of the nice green lake and the trees and the bear and all the... Okay, yeah. So, organisms get their energy from eating other organisms, and they're going to be transferring energy to each other. But it doesn't happen in a random way. There is a structure to it, and that structure is going to be our food chain or our food web, and is going to form the basis for our trophic levels. So trophic just means feeding, right? We're talking about animals feeding on each other. And we can come over to our diagram here, and we can look at the different trophic levels. So our first level, right, is these things that feed on the sun, right? It's not coming from other life. We call these producers, right? Because they're producing the bulk of the raw foodstuffs and organic material, living material, to begin with, right? They take in that energy from the sun, right? And we've got our primary production of living stuff. Awesome. We've got our primary consumers, right? Primary as in first level. Consumers as in they eat other life, not the sun. But importantly, really important for us to remember, is that as we move from one trophic level up to the next thing that eats it, about 90% of the energy is lost along the way, right? In this case, heat loss, right? So only 10% of the original energy from this base trophic level makes it up to the next level of the thing that feeds on it, right? The rabbit. And in turn, what feeds on rabbits is going to be our secondary consumers, our predators, things like snakes, right? So this is going to cut it in tenths again, right? The snake only gets 10% of the energy that the rabbit gets, which is only 10% of the energy that it got from the producers. And finally, at the very top of our food chain, our top trophic level is going to be what we call tertiary consumers, right? So these feed on other predators. Now, we can understand something about this, right? We've got energy that vanishes by a factor of 10 when you go up, and so you have comparatively much fewer organisms as you move up the chain, right? We can only support so many rabbits, right, based on the number of plants we have, and that number of rabbits determines how many snakes we can support, right, which is going to be far less. And this is part of the reason why, really, despite all the attention paid to predators, there are very few of them in the natural world in terms of abundance compared to how many rabbits, right, how many individuals that we have at these other trophic levels, right? So this is just going to lay out all those terms that I've mentioned, with maybe one of them added, right, which is our decomposers, which we'll look at in a bit. Altogether, this constitutes our energy pyramid. Why a pyramid? Because it gets smaller, rapidly smaller, as we move up. Okay, now, this is a very simple food chain, right? Each link leads to another, but in reality, we're going to get a food web, right? So very rarely in the actual world will animals just feed on one thing, right? They're going to feed on a lot of stuff. And so we have to construct something a little bit more complicated, which we call a food web. So the plants, right, we draw an arrow when it gets eaten by something. It gets eaten by grasshoppers and squirrels. Squirrels get eaten by the fox and the eagle, right? Grasshopper gets eaten by the scorpion, gets eaten by the fox. Okay, so our point is that we took what was a simple singular chain, and then we have to branch it out a little bit to talk about a real environment. And an actual food web and an actual ecosystem, real thing, is going to be 100 times more complicated than this, which is why we make it into a whole web, right? Which is made out of these individual food chains. Now, we have these terms which we'll need to establish, and we'll see a relationship between these terms and those trophic levels, which we just looked at, right? So some stuff eats just plants. These are going to be our herbivores. Some stuff is going to eat meat, right? Other living things are carnivores. Some things are going to eat both, our omnivores, like our coattamundi. Some things are going to be scavengers. Now, truth be told, hyenas are scavengers and predators as well. They're going to do a mix of both, not just scavenging. And then in our last category, we have detritivores, right? So in this case, instead of breaking things down by trophic levels, we distinguish them based on what these animals eat. But we can also see a clear relationship between this and those trophic levels. So our herbivores are going to be what primary consumers, carnivores tend to be secondary consumers, omnivores, right, tend to be secondary, but in this case we see a mix. Scavengers tend to be secondary consumers, detritivores are a little bit special, right? So these detritivores are going to be eating dead stuff, right? So we can look at our food web example here, right? So we've got our plants, primary producers, right? They feed our primaries, primary consumers, which feed the secondary consumers, which feed our top level predators, our tertiary consumers. And as these things die, what happens to their bodies? They're broken down and turned into nutrients by the process of decomposition. And the vast majority of decomposition is going to occur as a result of these three, right? So our fungi, our bacteria, and our earthworms. And we'll remember, right? Arrow means that it gets eaten, right? So this stuff, the dead stuff, right? Waste and dead bodies and corpses, right? Is going to get eaten by fungi. Fungi get eaten by the earthworms. And the earthworms, as we'll see, have a very important job of both eating the dead stuff and breaking dead stuff down. So we've got this distinction also to draw, right? We've used this term detritivore and decomposer. Are these the same? They are different. So detritivores eat dead stuff like our crabs. Decomposers break the dead stuff down and then eat it. Now something can be a detritivore and a decomposer like our worms, but it's important that we don't think of these as being totally interchangeable. Okay, so now we've talked about mostly feeding relationships, and we get to move on to the more complicated relationships that aren't just feeding. So that's going to be our next section.